So what the first section in this booklet has shown us is that we can categorise whether some substances are soluble or insoluble. So you got this idea of a difference between the two by using the back of our periodic table to work out which one is which. That's not the perfect whole picture though, because we got this question about solubility. Let's say we've worked out that something is soluble. That's not the full picture because it doesn't really tell us how soluble it is. This might not be something you've looked at or thought about before, but not every soluble substance is as soluble as each other. In other words, some soluble substances are very, very soluble in water, so you could dissolve a lot in a beaker of water. However, some take quite a lot of effort to dissolve, and you have to stir for ages, have to heat them up, etc. to get them to dissolve. So it's not a case of simply saying it's soluble. You want to know how soluble it is. And that's probably what the rest of the book is mainly about, describing how soluble different substances are and doing calculations with that. So the next question we turn to is, okay, so if we want to work out how soluble something is, how do you actually describe that? Because you need some kind of fair comparison that's going to allow you to say substance A is very soluble or substance B is not very soluble in water. So generally what we're looking at is this definition here. It's quite a complicated definition, whilst it's not very long. This actually does come up in exams as a 4-mark definition, which might surprise you. It's because there's lots of very specific parts to the definition you have to get exactly correct. So what we mean by solubility of a substance, it's the mass of solute, so that's the solid you're talking about, needed to saturate 100 grams of water at a particular temperature. So as I said, there's lots of very specific words and terms you have to get right there. The mass of solute needed to saturate 100 grams of water at a particular temperature. So most of it's generally okay. Mass of solute is a fancy way of saying mass of solid. We'll come back to saturate, that's probably the only thing that's a wee bit complicated. We're using 100 grams of water. That just makes it a fair comparison. You have to keep the amount of water kind of constant. And particular temperature we talk about, generally the solubility is going to be different depending on the temperature, so you have to kind of quote the temperature you're doing your experiment at. This idea of saturate though, this gives us a measure of how well something dissolves. What we mean by saturating is this. If we look at this diagram down here, let's play out the scenario in this definition. Let's say I've got 100 grams of water. So to calculate the solubility of a particular substance on the spatula, I want to see how much of it I can get to dissolve in 100 grams of water. And that'll give me an idea of how soluble it is. So I'm going to add a few wee spatulas. I'm going to stir it around to try and get it to dissolve. And generally it will dissolve with a wee bit of work. However, at a certain point, if I add more and more, I physically can't get any more of it to dissolve. So no matter how much I stir it at that temperature, I can't get all wee bits of solid to disappear and dissolve in the solution. At that point, where the solution is holding as much of the solid as possible, I can't get any more dissolved. That's what we call a saturated solution. You've got a wee kind of sub-definition here. A saturated solution is one in which no more solute, which means solid, will dissolve at that temperature. So it's physically impossible, unless I heat it up, which I'm not allowed to at that temperature, to get any more dissolved in it. So going back to this definition, to make sure it fully makes sense, if solubility is the mass of solute needed to saturate 100 grams of water at a particular temperature, putting that in simpler terms, which is not what I put in the exam, I put this exactly word for word in the exam, but a simpler way of maybe understanding this would be, what we mean by solubility is it's the maximum mass, the maximum amount of a solid that dissolves in 100 grams of water. So basically we're describing how much can I get to dissolve in 100 grams of water, just put in slightly more scientific terms in this definition, which you need for your exam. So, if we've got like two values, let's just actually do an example to see if that makes sense. So how it's going to be quoted is in units of this. Units are grams per 100 grams of water. Again, might sound a wee bit strange, but it's easier in context. So if we had a compound KCl, potassium chloride, its solubility value is 34.2 grams per 100 grams of water. What that means is if I get 100 grams of water and I get some potassium chloride, I will only be able to dissolve 34.2 grams of that potassium chloride in 100 grams of water at that particular temperature. This sentence is making the point that the temperature at which a solubility value should always be given. So in this case, that 34.2 is at 20 degrees C. As we'll look at later on in this booklet, the solubility values will change depending on the temperature. So it might go up or down depending on how hot it is. So at 20 degrees C, I can only get 34.2 grams dissolved in 100 grams of water. The higher the value is, the more soluble the salt is. The lower the value, the less soluble it is. So that's our definition. It's quite an important one. You get a lot of marks for getting it correct, and just make sure you're happy that you understand what it's actually describing and its units. So now we get on to what we call solubility calculations. So we're going to start quite simple and then work our way up. For these calculations, it's important that you remember the definition of solubility. We've emphasised that quite a lot. Also be aware 100 centimetres cubed of water weighs 100 grams. So that may or may not be a definition you're familiar with. If I've got 1 gram of water, it actually has a volume of 1 centimetres cubed. Therefore, 100 grams of water will have a volume of 100 centimetres cubed. While that's there, sometimes it can be a bit sneaky in questions. You might be quite prepared that the definition should have 100 grams of water. They might give it to you in a question as 100 centimetres cubed of water. That might be confusing, but you just have to remember 100 centimetres cubed is the same thing as 100 grams of water, so it works in our definition in the same way. Here's an example of a very simple calculation you might have to do. Calculate the solubility of potassium sulfate when 25 grams saturates 50 grams of water at 40, it should be 40 degrees C, we typo there. So this might seem a wee bit confusing. It's telling us how soluble it is. It tells us that 25 grams saturates 50 grams of water. So you might be thinking, well, that's just the value there. But again, going back to our definition, we have to express it in terms of how much saturates 100 grams of water. So as we're going to see through this booklet, most of the calculations we have to do generally involve scaling or like using ratios. What I mean by that is the questions told us that 25 grams of potassium sulfate will dissolve in 50 grams of water. I need to express it in units of how much is going to dissolve in 100 grams of water. So we bit kind of ratio work. To get from 50 grams of water to 100 grams of water, I times by 2. Therefore, if I have twice as much water, it's going to be able to hold twice as much solid. So I'm going to times the 25 by 2 as well. That gives me a value of 50 grams per 100 grams of water at 40 degrees C, which is what the question was asking for. That's expressing that value in proper solubility units of grams per 100 grams of water. So what we see in the next page is kind of a little exercise page of a little bit of practice of manipulating some solubility values. Might seem a wee bit basic, a wee bit boring. I would recommend doing all these questions though, because it does get slightly harder towards the end, and if you're not really confident on these kind of conversions and ratios on this page, you might struggle a wee bit later on. So we'll do your first couple examples, then maybe get you to pause and have a go with them yourself. So question 1 is a similar kind of question. Calculate the solubility of ammonium carbonate if 75 grams of it saturates 150 grams of water at 30 degrees C. So what the question told us here, I can get 75 grams of that solid to dissolve in 150 grams of water at 30 degrees C. Again, that's not the proper solubility units. It should be grams per 100 grams of water. So I'm going to have to use a wee bit of ratio work to work out what would be if it was only 100 grams of water. So depending how you want to do it, I'm just going to look at the 150. To get 150 grams of water down to 100 grams, easiest way is if I divide by 3, which gets me 50 grams of water, then times by 2 to get me 100 grams of water. So to get 100 grams of H2O, I divide it by 3 times by 2. Therefore, I'll write that here. I'm going to do exactly the same thing with the 75 grams because I have to use the ratios for both parts of it. So dividing 75 divided by 3 times by 2 gets me 50 grams of water, 50 grams of the solid per 100 grams of water. That is just the answer. To make it properly precise, I should say at 30 degrees C. Question 2, do this one for you as well. Potassium chloride has a solubility of 13.9 grams per 100 grams of water at 40 degrees C. Mixture A contains 8 grams of it in 50 grams of water at 40 degrees C. Mixture B contains 20 grams of it in 200 grams of water. Are A and B saturated solutions? So a little bit more of an interesting question here. So it's not always going to be saturated. If I've got less solid dissolved than I possibly can, then it's not actually saturated because it could take a wee bit more. I could dissolve a bit more in it. However, if it's got more than what it can hold, therefore it is fully saturated, and there's going to be some solid sitting at the bottom. So let's kind of analyse it. The key thing is the solubility value. At 40 degrees C, I'm able to hold 13.9 grams of potassium chloride in 100 grams of H2O. That's the key value I'm going to refer to. I've got two mixtures described, two kind of solutions. In A, I've got 8 grams of it, but it's only in 50 grams of water, so I can't compare like for like just yet. And in B, I've got 20 grams of it in 200 grams. Again, that's not the same units, I have to do a wee bit conversion first. I'll do A first. 8 grams per 50 grams of water, I'm going to scale that up to make it out of 100 grams. So that would correspond, if I had 100 grams of it, of water, it would be containing 16 grams of the salt. And with B, it's too big, so I need to convert it down. So 200 grams of water, turning it down to 100 divided by 2, would be 10 grams per 100 grams of water. So I've now got in units I can kind of compare fairly. So what I'm trying to work out here is, are these solutions saturated or not saturated? Do they have more than what can be dissolved or less than what can be dissolved? If I look at my key value here, what I've been told is that potassium chloride dissolves 13.9 grams of it per 100 grams. If I had a mixture which contains 16 grams of it, it's got more in the beaker than can possibly be dissolved. So there's going to be some solid left at the bottom of the beaker and a fully saturated solution. So therefore, this one is a saturated solution. It contains more solid that can possibly be dissolved at a temperature. Therefore, I can't dissolve any more. Therefore, it's saturated. However, by contrast, if I look at solution B, it's 20 grams per 200, which is the same thing as 10 grams per 100. That's less solid than 13.9 grams. Therefore, this solution, I could dissolve a wee bit more in it. Therefore, it's not saturated. Just to clarify one thing about ratios, you are a wee bit kind of flexible with how you approach this. I'm just doing one way. What I could have done for this question, I kind of scaled these to 100. I could scale 100 down to the values in A and B. In other words, I could have converted 13.9 grams per 100 grams of water down to 50 grams of water to compare the 8 to that value. So you can scale your solubility value down, or you're kind of working out values up. Either way will work in the question. So have we go at question 3 and 4, then I'll run through the answers very quickly at the end. So let's have a little look at the answers to question 3 and question 4. So for question 3, it tells you that the solubility of potassium chlorate is 25 grams per 100 grams of water. It's asking you to work out what mass of that will saturate 200 grams of water or 50 grams of water. So it's a wee bit kind of ratio work again. For part 1 of part A, if I know that to saturate 100 grams of water, I need 25. If I want to saturate 200 grams of water, which is twice the amount of water, I need twice as much solid. So 25 times 2 is 50. For part 2, I'm asked to saturate 50 grams of water, which is half as much as 100. So divide by 2, 25 goes down to 12.5 grams per 50 grams of water. For part B, it's kind of all the way around. I'm asked to work out how much water would I need to dissolve a certain amount of solid. So if I know that I need 100 grams of water to dissolve 25 grams of solid. If I'm asked to dissolve 5 grams, that's a fifth of the amount of 25. So you need a fifth of the amount of water. So 100 divided by 5 is 20 grams. If I'm asked to dissolve 100 grams of water, that's 4 times 20. Sorry, if I'm asked to dissolve 100 grams of the solid, that's 4 times 25 grams, which means 4 times the amount of water. So 100 goes up to 400 grams of water. With question 4, we're given information about potassium dichromate. At 30 degrees C, its solubility is 18.1 grams per 100 grams of water. Explain the mixtures below were saturated or unsaturated. So if the solubility is 18.1 grams, I'm going to do some conversions to convert these values into values that look like 100 grams. So 3 grams and 25 grams is the same thing as 12 grams per 100 grams. I'm timesing both sides by 4 there. I'll come back to the answer. Part B, 59 grams per 300 grams, divide by 3 to get out of 100 grams. That gets 19.7. Then part C, 7 grams per 50 grams times by 2 gets me 14 grams per 100 grams. So I've converted all three values into values out of 100 grams of water to make it comparable to the solubility figure. So analysing those values, remember the key thing is, if I've got an amount of solid which is less than the solubility value, it means I could dissolve more at that temperature. It's not fully saturated. If I've got a value which is bigger than the solubility value, it means I've got more solid in that beaker than I can possibly dissolve. Therefore, it's fully saturated, and it's more than saturated. It's got some solid left at the bottom. So we're going through my values. 12 grams is less than 18 grams, therefore A, it's not saturated. 19.7 grams is more than 18.1, which therefore means saturated. And the final one, 14 grams per 100 grams, is less than 18, therefore it's not, hasn't got as much as it fully can dissolve, therefore it's not saturated.